Today we will discuss about the work energy theory. So far we calculate the work, how to calculate the work and how to calculate the energy. So we have studied all those things. Now we apply the concept of work energy. The work energy theorem is a popular theorem so that you have to apply to solve some of the interesting problems that cannot be solved with the knowledge that we have already. Okay, that is with the help of Newton's law of motion or the kinematic equations. We may not solve some of the numerical which has to be solved with this theorem. So that means you should know how this theorem works. Okay. So let us do this analysis. Let us say there is a system. So inside the system, there is a spring, there is a block, and we are pulling the block with a force F. So this F is our external force. Okay. Now since the block is there, so because of this block, the mg is acting downward. So this mg is the gravitational force. Okay. And spring is there, so another spring force is there, kx type of force is there is a spring force. Okay. So friction is there. So that means you are pulling the block, that means friction is acting downward. So friction is there. And on that other side, you are applying another external force F2. And you are keeping the entire thing in a lift. So let us say the lift is moving, you are observing the entire thing from the lift, and lift is moving with the acceleration of a0, and entire system is moving with some acceleration a. Okay, so that means the various types of forces are acting on this body of mass A, and what is the effect of these various forces I want to calculate. Okay, so let us say you apply the Newton law. So in the Newton law, once you apply it, I want to write the net force, F net, should be equals to our mass into acceleration. This is the equation that I am going to apply. Okay. Now, what is net force? Net force here is the external force. First force is the external force. Then I can write another force is the spring force. F, let us say spring. Then there is the gravitational force is the Hg. Okay. Then there is the friction force is the, let us say, Fa. Plus, there is another force that is called pseudo, because I am moving in a non-inertial frame of reference. So for myself, for the observer, the system has some kind of pseudo force also. So let us say the pseudo force is Fp. Okay. So these are the different forces acting on this object, and resultant effect of all these force, that is the net force, that should be equal to mass into acceleration. Okay. Now what is acceleration? Acceleration is basically because of this external force and all the other forces present over here, the particle, let us say, displaced by a distance of y. Okay, let us say the particle is displaced by a distance of y. So can I write A into A? A means du dv dy. Yes. Du dv dy. So that is the acceleration written in terms of dv dy. So this is the final form of the equation where I want to apply this equation to get the work energy theory. So for that, what I am doing, we cross multiply dy. So ultimately what we got basically F external into dy plus F spring into dy plus F gravity into dy plus F friction into dy plus F pseudo force into dy. So all dy's are multiplied with this left hand side part, and that should be equals to A into d dv. Now once you integrate both the sides, so if I integrate the left hand side and the right hand side, so integration of F dot dy will give the work done. So here also give the work done, here also give the work done. All are giving the work done. So here I am writing the work done by the external force plus work done by the spring force plus work done by the gravity force plus work done by friction force plus that is equals to m into integration v dv. So if I take m common, so m is outside. So starting from initial velocity m to v, that is it gives d square minus u square by 2. Okay. So now we know that work done by spring force and work done by gravity, these are the conservative forces. These are the conservative forces. So I can write this as work done by conservative force. Plus work done by friction is the non-conservative force. Friction is the non-conservative force. Plus work done by pseudo force is there. plus work done by external force. So these are the different work done that I am getting, and that should be equals to how much? That should be equals to half into mv square minus half into mu square. What is this number? That is the final kinetic energy minus initial kinetic energy. So what I am getting, that is equals to K final minus K initial. So what is the left hand side? Left hand side part is the net work done, W net. Total work done by all the forces that present in the system that gives what? Change in kinetic. So this is the essence of the work energy. So in the net work done category, what are the different work done that are possible? I have taken all the effect of different forces. So in a question, there might be some forces that miss. So if the external force is not there, then the work done by external effect will not come. So conservative forces are there. So for that conservative force, what is the work done by the conservative force? That you have to know. And there is a non-conservative force also may be there. And there may be pseudo also there. So taking into consideration of all the forces in together, we can get the expression for the work energy theorem, and that is known as the final work energy theorem. Now we have to modify this. How to modify this? Now let us say to apply the work energy theorem, work done kinetic energy has to be taken in the same frame. Why? Because we know that work done depends on frame, and since inside the kinetic energy the velocity component is there, now velocity is also dependent on frame. So both the work done and kinetic energy has to be taken in the same frame, since both depend on frame. And we can apply the work energy theorem in non-inertial frame also, because in this situation, I have to take care about the work done by the pseudo force also. Okay. So in a particular situation, if I say the conservative work, we know the conservative work is how much? Minus of delta. Okay. We know that conservative work is minus of delta U. What is the delta U? That is equals to minus of U final minus U initial. This is the form. Or I can say this U initial minus U final. Okay. So if I use this expression in our initial work energy theorem equation, in that equation, what is there? There is the work done by the external plus work done by the non-conservative force plus work done by the pseudo force plus work done by the conservative force, that is equal to K final minus K initial. Now instead of writing work done by the conservative force, I can write the expression of the potential energy also. So WC is nothing but Uy minus Ua. That is equals to K final minus K initial. Now if I take Ui and Ua from the other side, so I am writing Ka plus Ua minus Ki plus Ui. That should be equals to work done. So work done by external plus work done by non-conservative plus work done by pseudo. Okay. So what it gives basically, this A final plus U final, that is the total energy, total mechanical energy. So kinetic energy plus potential energy is known as the total mechanical. So this is written as the E final. What is E? E is the total energy. So total energy what? Total energy is basically sum of kinetic energy plus potential. If I add the kinetic energy and potential energy, then I am getting the total energy. So finally what I am getting, this is the final equation. So in this equation, I am omitting the work done by the pseudo force. If I work done by pseudo force is included, then you have to add one extra. Okay. So this is the another form of the work energy theorem, where I am writing work done by external force plus work done by non-conservative force equals to the change in mechanical energy. E final minus initial is for the total energy or mechanical energy of it. Okay. In a particular system, if only conservative forces are exist, so no other forces are existing, that means work done by external is equals to 0. Work done by non-conservative, that is also equals to 0. Work done by pseudo, that is also equals to 0. That means no other forces other than the conservative forces are there. So in that situation, left hand side of the equation becomes 0. That should be equal to E final minus initial. Okay. So that means what I am getting, E final equals to E initial, or what I can write, Ui plus Ki, that is the initial total energy, that should be equals to final total energy, that is E final plus K final. So this is the modified version of the work energy theorem, and that can be applied only when there is no forces other than the conservative forces are present. Now what are the conservative forces? Now for this part of the segment, we mainly deal with the two different forces, that is the gravity and spring. Okay, gravity and spring. Because now we learn about these two forces only. So we don't consider the effect of electrostatic force. Why? Because the electrostatic force is another kind of conservative force, but that concept of electrostatic force will come inside the class 12. Okay, so inside the class 11 part, whatever the problem that comes in our exam or any question, so it mainly deals with these two types of conservative forces. Either it may be gravity or maybe spring. In some situation, maybe only gravity is existing, so accordingly you have to take care about the gravity force. So whenever the conservative forces are coming, so you don't have to calculate the work done by these conservative forces. Why? Because work done by the conservative force is nothing but the potential, negative potential that we have already learned. So that concept we can use, and I can get this equation, and that equation has to be applied. This equation has to be applied only when the forces are there, and that forces are only constituted. No other external forces acting on the body. No non-conservative force like friction, tension, all are not non-conservative force. So those are not there. Pseudo force is not there also. Okay. That means for this simple equation that can be applied over here in this equation. Okay. Now we go for the analysis of this equation. Step by step, we go inside the application of the work density theory. So first, we solve this type of problem. There is a ball which is being dropped from a height h above the ground, and you are asked to calculate the velocity with which it will hit the ground. Now, this problem we have already solved in case of kinematic situation where we use the simple motion equations. Now I am solving this equation using the work density theory. Now, in order to apply the work density theorem, first of all, you have to understand what are the forces acting on this particular body. So on this body, only energy is acting, that is the gravity is acting. So only one conservative force is there, that is the gravity. Okay. So since no other force is acting on this particular system, so can I write Ui plus Ki should be equal to Ua plus Ka. So initial potentiality should be equal to initial potentiality and kinetic energy should be equal to sum of potentiality and kinetic energy at the final situation. Now what is the initial? Initial is this position. And finally the ball will come down. Okay, so final position of the ground. See, so whenever I want to apply this equation, I have to take one reference. So every time you assume this ground is acting as a reference. So this is our reference line. So any point lying on the reference line, potential is 0. Any point which is above the reference line, potential is dot. Okay. So initial potential is how much? Initial potential is positive number, that is mgh. Kinetic energy is being released. So initially u is equals to 0, that is the speed is 0. So kinetic energy is 0. Finally, potential energy, so finally the ball is touching the ground. So final potential energy is 0, and final kinetic energy is equals to half of v square. Okay. So solving this, I am getting v equals to under root 2g. This is the same equation that we have already got whenever we apply this equation of kinematics equation to solve this table problem. But here I am using the concept of work energy theorem to get the same result. Okay. Moving to the next situation. Now there is a block of mass 1 kg. It has been dropped from a height of 5 meters above a spring. The spring is there. So now we understand that since spring is there and the mass is the block is there, now the two conservative forces comes in the picture. One is the gravity and the spring. Now block is released from a certain height. Release means initially the kinetic energy is 0. Find the maximum compression of the spring. Okay, maximum compression of the spring. So you have to understand this question very carefully. Why the maximum compression takes place? So let us say this is the point A from where you drop the part. Now this is the point B where it's just touching the tip of the spring. So at point B there is no compression of the spring. So if I apply the work energy theorem between point A and B, I can get the information of the velocity at point B. So initially I apply the work energy theorem between point A and B, taking, let us say, taking this is the reference line. So I am taking A is the reference. So B is below this. So for B the potential energy will be negative. So I am applying the work energy theorem between A and B. I am writing UA plus KA should be equal to UB plus KB. Okay. So UA is how much? 0. K is what? Is also 0. What is UB? That is minus mg into 5. Why 5? Because h is 5. And kb is the velocity at B point, that is half m dv square. Okay. So from that what you can get, that dv equals to under root 2g into 5. That is 10 into 10 root means 10 meter per second. So the block will strike the spring with a velocity of 10 meter per second. Now after that what happens? So at this point, once the block is touching the point B, so velocity of the block is downward with a velocity, it is moving down with the VV. Okay. Now, once it going from point B, Now the spring is in compressed. So spring is compressed means what? Spring is compressed means for this particular block, if I draw the block, let us say this is the block B, towards the reaches point B. At this point, the mg is acting downward. So mg number is how much? Mg number is 10 Newton. So 10 Newton is a fixed force that is acting vertically downward. Now once it starts to move from point B towards the downward direction, now the spring force will be in active position for K. So initially the Kx number is 0. Initially at point B, the Kx number is 0. Why? Because the spring has not started any kind of compression. Now as the block is moving downward, the Kx value will increase. But what happened? So let us say I want to move up to point C, where I am saying the velocity of the block is equals to Kx. That means at this point C, I am saying that the mg number is equals to Kx number. Why? Because initially the Kx number is 0. So ultimately the Kx will go on increasing, and ultimately Kx will match mg. So let us say this number is x naught distance. X naught distance, I want to calculate the x naught number up until which the mg becomes Kx. Why? Because initially the spring force is 0, and at point C, once the particle will come at point C, now I want to check that mg is equals to 10 Newton, and Kx also becomes 10 Newton. So between B to C, net force is acting vertically down. So between B to C, the particle is moving some kind of acceleration downward. So that means whatever the velocity of C is there at point C, the particle has a velocity Vc which must be more than Vv, which must be more than. Okay. So that point C I want to calculate. What is the velocity at point C? Now if I apply the work density theorem again between B and C, let us say I am applying the work density theorem between B and C. So I am writing UV plus KV should be equals to UC plus KC. Okay, UC plus KC. So for that I want to calculate what is the X naught. What is the X naught number? How to calculate that? So at point C, both the forces are balancing each other. That means I can write at point C, X naught is the spring force from that is balanced by 10 Newton. So what is X naught? X naught is also 10 by K, 10 by 50. That is 1 by 5. So the distance between B and C is 1 by 5 meters. So at point C, I want to calculate what is the velocity. Again, I am taking the reference at point B. Again, I am taking the reference at point B. So UB is 0. And what is KB? KB is a half mv square, that we have already got it, half mv square. And what is UC? UC is basically the gravitational potentiality, and along with that the spring will come. Now from the reference point B, I am moving downward, so it is minus mg into x naught. Okay. And spring has the initial potentiality equal to half kx naught square, and that the value of half mvc square. Okay. So I am applying the work density theorem between B and C. At point B, there is no potential energy. Why? Because I am saying the reference line is on the B point. Kinetic energy at point B I have already calculated. So corresponding to that, now we can calculate the Vc square number. So if I calculate the Vc square number, so all the half will cancel out. So ultimately what I am getting, Av square plus 2g into x naught minus k into x naught square by m. That will be the value of Vc. So clearly it is obtained that the Vc number is more than Vv. Why? Vv square is how much? Vv square is 10, means 100, plus 2 into 10 divided by x naught means 5, minus k means how much? 50, into x naught square means 1 by 25, into mass is 1. So that means I am getting 100 plus 4 minus 2, that means 102. Okay, so Vc square is 102, that is Vc is root of 102. So that velocity at point C is more than the velocity at point B. Now what happens after that? Now the spring will further move from point C, because at point C the particle is not at rest. So at point C what I am getting? The maximum velocity. Maximum velocity. After point C what happened? Now the Kx is more than 10. Now let us say the particle is going up to point D. Up to point D. Why it is going up to point D? Because between C and D, now the velocity is reduced. So there is a retardation. So acceleration negative. That means the velocity will reduce from Vmax to 0 at point D. Velocity at point D will be 0. So until and unless the block is at rest, the spring is compressed. Why? Because between C to D, the spring force is going to increase. So initially at point C, the spring force is 10. From C to D, the spring force is going to be increased. So increase means the upward force is more and downward force is fixed at 10 Newton. So downward force cannot be increased. So because of that, between C to D, once I am moving, that means the velocity has to be decreased. Now I want to calculate what is the x length. Let us say this is the x. I want to calculate that. So again, I am applying the work energy theorem between C and point D. If I apply the work energy theorem between C and D, so I write taking the reference at C point. Here I am changing the reference at C. So I am writing UC plus KC should be equals to UD plus KD. Okay. Now what is UC? UC is 0. But spring is compressed. Spring is compressed by external gravitational potentiality is 0, but spring potentiality is there. That means I have to write half K into X naught square number. Okay, Kc is how much? Half M into Vc square. I have already calculated the Vc square number. Now what is UD? At point D, gravitational potentiality is equal to minus mg into X. And spring potentiality is equal to how much? Half K into X plus X naught square. Why? Because every time you have to calculate the spring potential energy, that is for that you should use the elongation or compression value from the natural. Natural length is at point B. Spring is natural length at point B. From point B, I am compressing up to D point. So what is the potential stored inside the spring? Initially the X naught number is there. Now there is another X number coming into the picture. So X plus X naught whole square. That is the spring potential energy at point B. And the kinetic energy is 0. Okay. So from this equation, if I solve this, so all the values are known, only thing is that X is unknown, so I can calculate the X number. Okay. So that means this is the further compression. So in this question, you are asked to calculate the maximum compression of the spring. Maximum compression of the spring. That means you want to calculate what is the X plus X naught. Okay. So your answer for this question will be, the answer is X plus X naught. I have already calculated the X naught and you have to calculate the X number. So finally you get the rate. Okay. So what is the logic behind this problem is that I want to emphasize the point that the maximum velocity will be at point C, not at point B. Okay. So in order to calculate, once we understand this question, now I can solve this in one way. Why? Because now instead of applying the work energy theorem multiple times, I will apply directly between A and B. I will apply directly between A and B point. So you have to remember that one point must be very clear to you that whenever you are asked for maximum compression, that means that maximum compression takes place at D point. At D point. Okay. And at that particular point, velocity at D point is 2, has to be 0. Okay. So if I apply the work energy theorem between A and D, taking A as the reference line and D is the final point, I can directly write the energy equation. So if I apply the same equation between A and D, right? So initial potential at A plus kinetic energy at point A, that's equal to potential energy at point B plus kinetic energy at point B. Now kinetic energy at point B is 0. Initial potential energy, that is also 0. Kinetic energy is also 0. So what is the final potential energy? That is the value of UD. So UD is what? So minus mg into 5 plus, if I say this number is, let us say I want to calculate the distance between B and D, let us say using one single variable, let us say this number is, let us say y or x prime. Okay. So how much displacement of the particle takes place in particle direction? That is 5 plus x prime. So 5 plus x prime is the potential energy with the negative sign gravity plus half k into x prime. Okay. So that number is equals to 0. So from that you have to solve the quadratic to get the value of x prime. And that x prime is nothing but what? X plus x naught. This is the same x prime that we. Okay. You can check that also. So only thing to understand that there are 2 points where the velocity is maximum and there is another point, the compression is maximum. Both are not the same. Both are not the same point. That's why I break the problem into different segments to get the feeling that where the point the velocity will be maximum and where is the point that is the compression will be maximum. Okay, so this is the classical example to apply the work energy theorem where you can get the idea to apply the work energy theorem properly between any 2 points. So whenever you select the particular point and between these 2 points you should apply and accordingly you have to write the equations. Okay. Now this equation, let us say there is another problem. So you are asked to calculate find the distance traveled by the block before it stops. What you are doing? So initially the spring is at natural length. Now there is a block, you compress the block by a 2 meter and you release from this position. Once you release the block, so now the block will be moving in the forward direction. So ultimately one point will come when the block will be over here and the block velocity will be 0, that means it is at rest. So you want to calculate how much distance it has been traveled before coming to rest. Okay, let us say this is the initial point, this is the final point, and taking this as the reference line, I am applying the work energy theory. Okay, again only the conservative forces are there. No, there is a friction. So I have to take care about the friction. So I have to modify your equation. What is the modification? So work done by the non-conservative force, only one non-conservative force is there. That should be equal to UF plus KF minus UI plus KI. This is our equation, modified equation. Okay. So what is the non-conservative force? There is a friction. So what is the magnitude of friction? So since the particle is moving, so friction is basically equals to mu K into N. What is mu K? That is 0.5 into N is how much? 10. Then 5 Newton force is acting as a friction. So friction is always acting in this direction. So friction is acting on the block is in this direction. Okay. And the particle moving in this direction. So work done by the friction is negative. So what is the displacement of the point? This 2, and I am saying, let us say this is the x distance from the natural length. I want to calculate this x number. So work done by the non-conservative force equals to minus 5 into 2 plus x. Why minus? Because friction is acting in the negative direction and the particle is displaced in the positive direction. So that is the work done by the non-conservative force. Initial potential. So initially there is no gravity potential because all the points are lying on the same horizontal line. So there is no effect of gravity. Only the effect of spring compression will come. So spring is being compressed by 2 meters. So it is equals to half K into 2 square. Initial potentiality. Kinetic energy is 0. Why? So it is not the initial. It is the, so let us say I have to write the final part. So initially, so finally, what is the potential energy of spring? So once the block is released, the spring comes to its natural length. So final potential energy is 0. Final kinetic energy is also 0. What is the initial potential energy? Initial potential energy is equal to half K into 2 square. Okay. And what is the kinetic energy? That is also equal to 0. That is also equal to 0. Okay. So initially there is no kinetic energy. Finally also there is no kinetic energy. So simply I should write this equation. So it gives how much? Minus 2K. So minus 2K minus 2 cancel. So ultimately I am getting 5 into 2 plus 8 should be those 2K means 100. So 2 plus 8 means 20. X is 18 meter. X is 18. So 18 meter is the displacement of the particle before coming to X. Okay. So here final potential is what? Final potential is at this location. Here. So once the particle comes to the final position, spring is in the natural length position. Okay, spring is not in the compressed position. So that means final potential is 0. And gravity is no effect. Why? Because all the points are on the same horizontal line. And kinetic energy is also 0 because the particle comes to a place. So only the initial potential is there. Initial potential is what? Half x square. What is x? That is 2 meter. Okay, it is given. So solving this, I am getting the x equals to 18 meters. So it will travel 18 plus 2, that means 20 meters. Before coming to rest. If I calculate the distance from this point, so from this point it has to travel by 20 meters before coming to rest. Okay. So in this situation, the particle is moved. So let us say the mass of the particle is m. You are moving the particle in a path whose slope is varying continuously with the force of A. So you are asked to calculate the work done by the force A when the mass reaches the topmost position. Okay. So initially the particle is over here in the initial position, this is the final position. So once you are moving the particle along the path where the slope is varying, you are asked to calculate the work done by the capital F. Now in the entire path the friction is active. So here the friction is there and the coefficient of friction is given as mu. Okay. Let us say for a very small distance path. So let us say I am focusing on this path. If I enlarge this, let us say this is the at this point where the particle is making an angle, slope is let us say theta. Slope is let us say theta. So for this theta position, let us say this is the theta angle. Let us say this is the particle. Okay, this is the particle. So I know that here the force is acting in this direction. So force is constant force A. And the component of force mg is acting downward. So one component, that is mg cos theta, is acting over here, mg cos theta, and that gives the normal value. Normal value. Okay. And here the mg sin theta part is also there. Mg sin theta part is there. Okay. So mg has two components. One is mg sin theta and another mg cos theta. Now let us say for this small segment of the path, let us say the point is marked as, let us say I am moving the particle from A to B point such that AB distance is basically our, this distance, let us say dx, and this vertical distance is suppose dy. Okay, I am considering a small track so that the particle moving from A to B. So inside that, what is the friction force? So here, since the particle moving, so friction is kinetic friction, that is equals to mu into n number. Now what is n? N is basically our mg cos theta. So mu mg cos theta is the friction force acting on this particle. Okay. So if I want to calculate the small work done by this friction force, so dw by friction force is how much? So that should be equal to friction is acting in this direction. Friction is acting in this direction. The particle moving from A to B, and let us say the AB length is, let us say ds. ds. Okay. So work done by friction is how much? Minus F into ds. What is that number? So minus mu mg ds cos theta. This is small work done. Now what is ds cos theta? ds cos theta can be treated as the dx number. Okay, so minus mu mg into dx. Okay, so this is the small work done in moving the particle from A to B by friction. So what is the total work done? So from this equation, I can get the total work done by friction is equals to integration of dwf. That is nothing but minus mu mg will come out and integration of dx. So what is the integration of dx? Integration of dx is the total length L. Okay. So ultimately I am getting that answer is mu mg into L is the work done by the friction. This is the first part of the problem. Now, what is the work done by the mg sin theta? That is the work done by the gravity. So work done by gravity. So let us say in moving the particle from A to B, let us say dwg is the work done by gravity. dwg is the work done by the gravity. So work done by the gravity is equals to mg sin theta is acting downward and ds is acting upward. So can I write minus mg sin theta into ds? Okay, minus mg sin theta into ds. So this is a small work done by gravity in raising the particle from A to B. So I want to calculate the value of total work done by gravity. That should be the integration of dwg. So that means it is minus mg and ds sin theta is what? ds sin theta is nothing but our dy. So integration of dy. So integration of dy gives the h number. So minus mg into h is the work done by the gravity in moving the particle from the I to the A. I am getting the total work done. Okay. Now in this question, you are moving the particle very slowly so that initial kinetic energy Ki is 0, final kinetic energy is also 0. Okay. So this is the condition that I am applying over here. So what are the forces acting on this? So work done by capital A plus work done by friction plus work done by gravity. These are the different forces acting on the particle. They are giving the work, and that should be equal to change in kinetic energy delta K. And delta K is what? 0. Delta K is also 0. So from that, work done by capital F should be equal to how much? Minus of work done by friction minus of work done by gravity. So I have already calculated the work done by friction and work done by gravity. And negative of that will be the value of minus mg common and h plus mu mg into L. Okay. So final answer will be mg into h plus mu L. Okay. So this is the answer of the problem. That is work done by the capital F is equals to mg times h plus mu. Okay. So whenever you are moving the particle in a curvy track where the slope is varying, so you have to do it in this way. Okay. You have to take the small part of the curved track and you have to analyze that track so that what are the forces that are doing the work. So I am not considering the effect of mg cos theta. Why? Because mg cos theta and displacement are perpendicular to each other. So mg cos theta has giving no work. Similarly, normal is also not giving any kind of work. Normally they can perpendicular. So only the work is given by this mg sin theta component and the friction and the capital. So three component of work are done. And total work done, so this is the net work done. Net work done should be equal to change in kinetic energy. And change in kinetic energy, we are assuming that is close to zero. Because there is a slight change in the velocity, and I can neglect that because the particle is moving very slow. Okay. So this is another application. So like this way, there are many more applications for this type of problem where I can apply this situation. Okay. Okay. Now come to the another set of situation. Let us say this type of problem. So there are pulley block system, but we have already solved this type of problem in the Newton's law of motion where there are two blocks are there. But in this situation, I am asking you to calculate the velocity of the block when they move a distance by x. So they are connected by a single string. If m2 is greater than m1, so m2 is moving downward by x distance. If I say m2 is moving downward by x, so m1 is moving upward by x. Okay, m1 is moving upward by x. So after some instant of time, there is a separation of 2x between them. There is separation of 2x between them. Now I want to calculate the velocity of the particle. You are asked to calculate the velocity of the block, and both the blocks are moving with the same velocity. Both the blocks are moving with the same velocity. Now, this type of problem can be easily solved using the work energy theorem. Why? Because I am not going to apply the Newton laws. What I am applying that this is the initial position. This is the initial position. And finally, after some movement, m1 comes over here, m1 comes over here, and m2 comes over here. So this is the final situation. Okay, this is the final situation. So you have to identify both the situation where the particles are. So now you have to apply the work energy theorem between initial and the final position. Now here also only the weight is acting, that is the gravity. So I can write the only the conservative forces are there. So I can write is that so total initial kinetic and initial potentiality plus initial kinetic energy should be equal to final potentiality plus final kinetic energy. Okay, and I am applying this not for a block. I am applying for a system. What is our system? System is the entire system. In this situation, the pulley is massless, so it has no mass. So I am only focusing on the two block M1 and M2. So what is the initial potentiality? So if I say this is our reference line, so initial potentiality is 0. And the blocks are not moving initially. System starts from rest. So they are not moving, so they have no kinetic energy 0. So what is the final potentiality? So final potentiality from the reference point, M1 block is raised by x distance. So for M1 it is mg into x. Not mg, M1g. Because it is M1. So final potentiality for the M1 block is raised by x distance from the reference line. So for M1 it is positive number. So how much? It is M1g into x. For M2 it is moving downward from the reference line. So it's minus M2g into x. There is a system potentiality. And what is the kinetic energy? So kinetic energy is both are same because this particle is moving with v, this particle is also moving with v. And since I am doing the energy calculation, so these are the scalar quantity, I should write half m1 v square, half m1 into v square plus half m2 into v square. Okay, v square. So that v is the same velocity for both the block because they are constant by a single string. They are constant by a single string. So if I change the sign, so what I am getting, so that should be equals to m2 minus m1 into gx. That should be equals to half v square into m1 plus m2. Okay. So ultimately, I can write v should be equal to 2 times of m2 minus m1 into gx divided by m1 plus m. m1 plus m2 whole v. Okay. So that will be the answer. 2 times of m2 minus m1 gx divided by m1 plus m2. So option number C is the correct one. Okay. So in this situation, I am not applying any kind of Newton law. What I am doing, I am applying the work energy theorem, but that work energy theorem is not applicable for a single block. I am applying for the entire system. So once I am applying for the entire system, so for both the block, we have to identify what is the new position and what was the initial position. Based on that, you have to write the potential energy. And once you write the potential energy, then try to write the kinetic energy. Okay. So there is another situation. Okay, this is another situation. Let us say there is a ball of mass 1 kg fired inside a circular pipe. So there is a ball which is being fired in this direction inside the pipe with the speed of 10 meter per second. So the ball will follow this track and ultimately it will come out from this track and it will go up to a height of h. Okay. So you are asked to calculate the value of h. So initially, let us say this is the initial position, this is the final position of the ball. Okay. So based on the initial position, if I draw a horizontal line from the initial position, so I am saying this is the reference. Okay. So first calculate the what is the position of the ball once it has been released from the pipe. So that h plus this number. What is this number? So this number is nothing but, so this angle is 37 degree. So this angle is 37. So 5 cos 37. This value is how much? This is 5 cos 37. 5 cos 37 degree. So that means 4 meter. Okay. So 4 meter. So now I apply the initial potentiality, let us say Ui, kinetic energy, Ki, that should be equal to final potentiality plus final kinetic energy. So taking the reference line from the I. So potentiality initially is 0. Kinetic energy is how much? Half A into V square. V square. Final potentiality is how much? Mg into 4 plus H. Mg into 4 plus H. And finally, the particle is at rest. So here the kinetic energy is 0. So it is 0. Okay. So A and will cancel out. So V square equals to 2G into 4 plus H. Okay. Now what is V? V is 100. V square is 100. 2G means 20 into 4 plus H. That means 4 plus H equals to 5. So that means I am getting H equals to 1 meter. So it will be raised by another 1 meter from this point. So your answer is 1 meter. Okay. So this type of problem that may not be solved with the help of simple knowledge of kinematics or Newton. So these are very good example problem we can solve using the work energy theory. Okay, it will make the easier. Okay. So this is another type of problem. There is a mass M which slides down and gets onto a plank of mass M. So small m mass is there which is at rest, which slides down on an inclined plane and ultimately touches the capital M at the base of the hill. Due to the friction between the mass and the plank, the disc slows down and ultimately both moves together. That means they are moving combined. Okay. So plank is rested on a smooth plane. And the once the particle is coming down, so let us say the mass comes down with a speed of v. So first you have to calculate what is the velocity with which the small m is targeting the or falling on the capital M. Okay. So for that, if we apply the work energy theorem between initial point and this is the final point for the mass small m. So here also in this situation there is no friction. Here mean is 0. Only the friction is acting on the block and the plank. So if I apply the work energy theorem between I and F position, taking this I as the reference position. Okay. So Ui plus Ki should be equal to Ux plus Ka. So what is Ui? Ui is 0 because I is on the reference position. Kinetic energy is also 0 because the particle starts from rest. Particle starts from rest. What is the potential energy? Potential energy is minus mg. Minus mg. And what is the kinetic energy? Kinetic energy is half mv square. So from that, I am getting that half mv square is equals to mv. Okay. And the v equals to under 2j. So this is the velocity with which the small mass m starts to move over the plank. Okay. Initially, the plank has no velocity. But once it strikes, now the friction comes into the picture. Now it is a block over block problem. Let us say the small m is there and on that block the capital M is there. Okay. So small m is trying to move in this direction with the velocity v. So friction is acting on small m in this direction. In this direction friction is acting. Same friction is acting on capital M in this direction. What is the value of friction force? That is equals to mu times small m into g. Okay. This is the friction force. So this friction force will act on the small m to reduce the speed. And that same friction force is acting on the capital M to increase the velocity of the m. And you are asked to calculate the common velocity. So let us say after t time, the small m has the velocity is equals to v naught. Let us say after t time, the small m is moving with the velocity v naught, and at the same time, the particle capital M is also moving the same velocity v naught. Why? Because the M, capital M, will accelerate and small m will retard. Okay. So what is the retardation value? Retardation value is force divided by mass. So A for small m should be equal to how much? Minus mu mg divided by m. That is equals to minus mu mg. And A for capital M is how much? That is plus mu mg divided by capital M. That is this number mu mg by m. Okay. So because of this, let us say after t time, the both the particle attain the common velocity. So V naught for, if I write for small m, should be equal to how much? V minus AT. That is mu g into T naught. Let us after T naught time. Now V naught value for the capital M should be equal to 0 plus mu mg by capital M into T. Why? Because the particle capital M is initially 0, initially at rest. Okay, so that means I am taking the number. So these two numbers are equal. So what is V? V equals to root 2G, that is also known. So if I solve these two equations, so that means I am getting root 2GH equals to how much? T naught take common, mu G also take common, which equals to 1 plus small m by capital M. Okay, that means with that T naught, now I can calculate. So T naught is known, that means after this much time, so root 2GH divided by mu G into 1 plus small m by capital M. After this much amount of time, the block and the plank are moving with the same. Okay. Now you are asked to calculate the common velocity. So that is you want to calculate that V naught number. So the V naught number for capital M, that is equal to how much? Mu mg into T naught. Mu mg by capital M into T naught. So you have already got the value of T naught. You put it over here. So you can get the answer for V naught for capital M. That is the same answer for the V naught for small m also, because both are moving the same speed. So first part is already done. Now regarding the work done by the friction, so friction is being, so because both the particles are not moving in the same distance. Both the particles are not moving by the same distance. Why? Because for the small m, let us say the displacement is S1. For the small m, let us say the displacement is S1. So what is S1? The S1 should be equal to Dt minus half A small m into T naught square. That is the displacement. Now what is the displacement for the S2? S2 should be equal to half A for capital M into T naught square. So both the numbers are different. Yeah, both the numbers are different. In fact, S1 will be more, S2 will be less. So there is a relative displacement between 1 and 2 until and unless the slipping stops. So you are asked to calculate the work done by the friction. So friction is doing work on small m and friction is also doing work on capital M also. So work done by the friction on small m should be how much? Should be equal to negative of minus mu mg into S1. Okay. Similarly, work done by friction on capital M, work done by friction on capital M should be how much? That is mu plus, it should be plus, because friction is acting in the forward direction, mu mg into S2. So you calculate the value of S2, you calculate the value of S1, you get the answer in for these two work. Now simply add these two numbers. So once you add these two numbers, so work done becomes negative, because S1 is more and S2 is less. So final answer for the work done by the friction will be a negative. So it will be a negative answer. Got it? So this is the idea behind this type of problem, where the two block problem is there, friction is there, along with the work energy concept is there. So all the concepts are mixed. Okay? So these are comes under the mixed variety of problem, where you have to solve different types of problem applying the different points. Okay. Got it?
Yes.
Moving on to the next segment. Now, so far we understand how to apply the work and theory. Now, another classical example of application of work and theory is the vertical circulation. So far we solve the circular motion, but that circular motion is the horizontal circulation. Once the particle is moving along a vertical circle, now the effect of weight will come, the gravity will come. So that means the concept of work energy will be added. Okay. So these are simple situations of vertical circulation. So these are the vertical circle performed. So once the particle is performing vertical circle, let us use the M mass. So M mass is going to be raised. Once the particle moving upward, once the particle moving upward, that means the work is done on the by the gravity. Hmm. So work done by the gravity comes into the picture. Okay. So that means I have to apply the concept of work done over here to solve this type of variety of problem. Okay. So what is the idea is that so there is a circular loop. So now I want to check whether the particle is moving along the circular loop or not. Okay. So for the vertical circle, the circular motion is always a non-uniform circle. Why? Because whenever the particle is performing vertical circular motion, so if the particle is moving from point A to B and then from B to C, so effect of gravity is always trying to reduce the speed. The particle cannot move the same speed. So if I project the particle with the u velocity, so at point B the velocity will be vb, at point C the velocity will be vc. So gradually the velocity will decrease. So since the tangential component of velocity is going to be decreased, so can I say the particle has an acceleration or retardation along the tangential direction, as well as it is performing a circular motion, but everywhere the radial acceleration is there and the tangential acceleration is acting downward. Okay, because acceleration is opposite to the direction of velocity, so that it will reduce the speed. So vertical circular motion is always a non-uniform circular. It cannot be a uniform circular motion. Okay. So till now we have discussed the motion of particle in horizontal circle. That is, gravity does not affect the particle. So you can clearly see that whenever I throw the particle from point A, the velocity is v1. As the particle moves to B point, the velocity becomes v2, then C v3, then D v4. So gradually the velocity is going to decrease. Velocity is going to decrease means why? Because the gravity is acting down. And that in that situation, everywhere the particle velocity is going to decrease. That means it has some kind of angular retardation. Retardation is there. That means the particle cannot follow a uniform circle. It should be a non-uniform circle. Okay. So vertical circular motion, effect of gravity has to be considered. Whenever we consider the effect of gravity in a circular motion, then that particular circular motion is known as the vertical circle. So for a particle moving in a vertical circle, it attains different heights with respect to ground at different point. So when the particle moving, so at different position, let us say this is the point A, this is the point B, this is the point C. At different point, the particles are located at different height from the ground. So these heights are different. So that means the potential energy at different points are different. So the potential energy of the body changes due to gravity in this type of motion. So this results in unequal kinetic energy. Why? Because the potential energy is going to be changed. That means it has to be go inside the kinetic energy. So kinetic energy will be different. And therefore speed of the particle changes during motion. And ultimately you can say it is a type of non-uniform circular motion. Okay. It is a type of non-uniform circular motion. So whenever I am discussing about the non-uniform circular motion, so there are two varieties of problem. So either the particle is connected to the string or the particle is connected to the rod. So what is the difference between the string and the rod is that, so for string, the tension can be zero. Tension can be zero. But for massless rod, here I cannot say tension cannot be equal. Here the tension cannot be equal to zero. So these are the two situations where we have to apply the concept of vertical circular motion, whether the ball is tied with a string or the ball is tied with a massless string. So I will explain the part. The velocity at maximum height cannot be achieved. Okay. So wherever the mass is attached to thread or mass is inside a hollow. Okay, right now these are not so important. Why? Because whenever I discuss about the numerical, then you understand why these concepts are there. Okay. So why the velocity at maximum height cannot be zero? Why it can be zero? Okay. So for this situation, this is the second situation, and this is the first situation. Okay. So these are typically useful for your notes, but in order to understand, I have to go inside this numerical part. Once I saw the numerical, then only you can understand why the tension is not equal to zero, why in that situation the tension may be equal to zero. And once the tension becomes zero, then velocity cannot be zero. If I say for this string, tension is equal to zero. So that means velocity is not equal to zero. But whenever I am saying tension is not equal to zero, that means velocity can be zero. So velocity can be zero. I cannot say that velocity is always zero. Or I cannot say velocity is always not equal to zero. but there is a tendency or there is a chance that velocity might be. So these are the two types of problems that are going to be analyzed for the vertical circulation. Okay.